Okay, so this is intended for physical oceanographers. Okay, so the let me think. Yeah, so I got many of my slides from my 100 level class. So hopefully that'll work. Okay. All right. So just before I get into the meat, there's some terminology about sensors we use. So I got this information from Spar's one of his report online. So in general, we use pressure gauges, but there are different kinds. Okay. So there's hydrophone and differential pressure gauges. These are for high frequency stuff. So they are measuring signals from earthquakes, like shaking. Okay. So these are not what we're talking about here. What we're talking about is low frequency, looking at deformation that include BPR, the bottom pressure recorder, and APG, absolute pressure gauge, and also A0A. So there might be different names, but these are the kind of three general terms we use. And you can think about APG as a improved version of BPR. Okay, and most of them use the pyroscientific sensors. I will talk about it. It has the issue. It's really good. You can put in like 6,000 meters depth, but it has a drift issue, and we'll talk about it. Okay. So and A0A is a calibrated. Basically, you have two sensors there in the casing, so you can calibrate the drift, and that's another main thing we'll talk about. Oh, I have only 30 slides. Okay, so we have plenty of time. If you have any questions, feel free to ask anytime. Okay, so this is intended to be more like informal. Okay, all right. So we geophysicists and geologists interested in the ocean because I think, okay, majority of the events are in the ocean. Okay, so the big one is subduction zones. Subduction zones we have earthquakes, tsunami, volcanoes, and for plate boundary, the spreading center, ocean ridge, transform faults. There are volcanism, seismicity, and other things, tectonic events, and then we got hotspots. So in the middle of the ocean, and some of hotspot, we got island, like people live there, hot, like Hawaii, Iceland, and in other places they're not. So we really care about it because it's very simple. Yeah, a lot of things happen in the ocean. Okay, so that's the main reason that geology and geophysics likes to do more in the ocean. Okay, so this is a little. So my intention of putting like this is okay. So on the top, on the left is a new Webb telescope. The last year or the year before, I forgot. So you can see that the improves the resolution from the middle one by I don't know, order of magnitudes. Okay, so you see much better. So I think in our field, currently for geodesy, so geodesy measures the deformation of the crust, our resolution is we're really good on land. So we have continuous GPS stations, we get INSAR, and there are also other instruments where we can measure deformation really well on land. Okay, but when you go offshore, if the event happens in the offshore, if it's not too far from land, we can still see it. So that's kind of lower resolution. But when it gets too really far, for example, in the trench where we care a lot about, we don't really have much resolution at all. It's dark. It's getting better, and that's why we have this workshop. That's why we have many projects going on for the last 10 years. But we want to do better. We want to change this to even better. Okay, so that's it. All right. So why pressure measurements helps? So the general idea is that if you put a pressure in the bottom of the ocean, okay, what you will see, there are tides, there are currents, there are many variations that you can see. Okay, these are mostly from the water activity. Okay, But when the seafloor moved, okay, for this one, my student draw this for slip on the fault, or it could be a volcano, it could be landslide, okay, all kind of stuff where you get a deformation. Then in theory, in your pressure measurements, you should see for example, in this case, because it happened really in a short time period, so it's almost like a step, okay. In other activities where long term, it might be just a trend, okay. So you should, in theory, you should be able to see these signals in the seafloor pressure data, and that's kind of what has been used. But the issue is, for a lot of cases, first there are drift issue. I'll show it later, where there's unknown drifting in the instrument where we need to deal with, and also some of the signals are relatively small, like millimeter or centimeter level over, let's see, 1 week or 2 weeks, or sometimes a few millimeter per year. That's what we wish to measure. And these small magnitude signals, when we think about this, the signal to noise ratio, in terms of signal noise ratio, is really low. So that's really difficult to do. So we want to improve our ability to remove water contribution to the seafloor pressure data. That's kind of our goal. All right. Okay. So here is one example. This is a project done between summers of 2014 to 2015, I think. Okay, so that's North Island of New Zealand, and they're offshore where SPAR was involved, and Laura Wallace was leading that. They have also some Japanese sites too, and they put seafloor pressure instrument over there and try to measure low slip event. I'll have animation to show what that is, but it's basically it's a fault motion in much slower than earthquakes. Okay, benign, but then as you can see on the right, so all these colors, these are all seafloor pressure data. Of course, it's detrended, it's got tide removed, and you can see here there are oops. Okay, so these are the water contributions, and then highlighted by these two kind of horizontal lines. This is meant to show the step of the event, and you can see the step is, for example, this one is this the y-axis is equivalent water depth in centimeters. All right, so the water variation in this case, the standard deviation is probably around 2 centimeters. Then the step is only like 3 or 2 to 3 centimeters for this site. It varies from site to site, but the signal is really small. But in this case, it's lucky enough, we are lucky enough we can see it, but still there are some issues. And then in comparison, the bottom line, okay, this is an on-land GPS station, MAKO, it's over here. And you can see for on-land, the noise is really, really small. Then the signal is really, you really see it. So if I can like envision that in the future, like maybe in 10 years, if we can remove signal, the noise here down to this, that'll be, crazy. That'll be very, very useful. All right. So one issue of this high noise is that it's hard to constrain the displacement at each site. So this is a study they're looking at. So they look at the seafloor pressure data, but they also use ocean circulation models and try to use a model to kind of remove some of the water contribution. And then their results where the magnitude, so the size of this pie shows the magnitude of slip at that site. And so this is from the original study, and this is from their study where after they look at the ocean water contribution, then they saw a significant difference in the magnitude of the slip. So this is really highlighted one of the challenges of the large water noise. Okay, another challenge is the high cost. So for us who do field work in the ocean, it's just expensive, right? It's a ship time. On average, 30 to 50,000 a day, US dollar. Okay, So for example, last October, we did a deployment offshore New Zealand. We were able to deploy 4 instruments in a 12-hour period. So for a day, we can only do 80 instruments total. So it costs ship time. And also instrument. So this is just I got this number from our colleagues in New Zealand. So for them, the instrument itself is about 40 to 50K per piece to just build it. That include battery, data storage, float, other things, and the sensors. Then they have some consumables you have to spend every year. Okay, so this is another challenge. Okay, so how can we reduce the cost? Or go ahead.
So is GNS the brand name or is it a type of APG?
No, GNS is an institution at New Zealand.
Thanks.
Yeah. Okay. All right. Okay, so another challenge is the drift. So as I said, most of these sensors, the deep ocean sensors, use the parascientific sensor. It's like this. It's like this big, I think. Okay, and it use these crystals. It's amazing how they can measure pressure really well. And this is one data that from a site. I think this is from probably in New Zealand. Okay, so here the blue lines are the tides. Okay, you see the tides, of course, the most dominant one, but tides can be relatively easy to remove. People might have different opinions. Okay, relatively easier. Okay, you can remove the tides, and that's you get the red lines. Okay, and the red lines, you notice there these kind of things. This is like a drift, like a trend. If you look at the magnitude of this thing, so this is 2 meters. So that's about 400 days, so about a year, less than a year, maybe like, yeah. In about a year, the thing drift about 2 meters. So whenever we take the seafloor pressure data by these instruments, we first need to do a I don't know, you have to assume what the line looks like, then just remove the drift, then work on the residuals. So this can be important because if you want to measure, for example, a long-term tectonic movement, a few millimeter or a few centimeter per year, from this data set, then you might, remove part of the signal when you do this fitting. So that's really a challenge. That's why the A0A is a calibrated, prevented. Okay. All right. So that's about the sum of the challenges. So next I will talk about the scientific targets. So most of them are earthquake and tsunami, and then the underwater vents and volcanoes. So I will talk about these two. All right. So first, subduction zones. Okay, so
now I'm good.
Randy told me that for physical oceanographers, Atlantic Ocean is much more interesting than Pacific. Is that true? No? Okay, I'm glad. Okay, but for geophysicists and geologists, okay, Pacific Ocean is definitely much more interesting than Atlantic. Okay, that's simply because all the subductions, or most of the subductions, are around the Pacific Ocean. Okay, we get the big earthquakes, the big tsunamis, the big volcanoes, they're all there. Okay, so that's kind of why okay, so that's kind of why. And so for example, one question, like, why do we do workshop on this topic right now, right? So the reason is really the 2011 Japan earthquake. Okay, if I want to put it very simple. So that's really the main reason. So if you look at this figure, this shows the major earthquake and tsunamis. When I say major, I mean really big ones. Okay, so in the 1940s and 60s, we have a few. So in 1964, the Alaska one, and the Chile one, 1960. So these are really two big ones. Then for 40 years, there's nothing. Okay, there's no no earthquake or tsunami like this size. Then all of a sudden, 2004, there's a big one in Indonesia. Then 2011, there's a big one in Japan. Okay, so the 2004 and the 2011 earthquake really pushed our field because we realized that we're really limited on measuring offshore deformation, and that's provide critical information for earthquake and tsunami assessment measurement. Okay, so these are really the driving force. So this is animation about. Okay, so how tsunami were generated in subduction zones. All right, hopefully, is that good? Okay, so all right, so in order to generate a really big tsunami, you need big deformation, okay, especially in the shallow part of the fault near the trench. Okay, so even if you have a big earthquake, but if it's relatively deep, there's no shallow slip near the trench, you're not going to generate big earthquake, a big tsunami. Okay, so but to monitor, like to estimate whether the likelihood of shallow slip is a challenge with offshore data.
Matt, you might mention what the geophysicists call a trench versus what the physical oceanographers might call a trench.
Okay.
So, in other words, the physical oceanographers would mainly be thinking about the depth of the seafloor, the very top of the seafloor.
Okay.
And that might be fairly flat across a geophysicist trench, which is where the plate is dipping down under, right? Could because it's gotten filled up with sediment.
Yes.
And that's something at least I had to learn that.
And when you talk about shallow, what's the scale of depth into the seafloor you're talking
Above 10 to 20 kilometers from the seafloor.
When we're talking about a tsunami,
Right.
the issue is that on a normal subduction zone, the part of the fault that's locked is typically fairly deep, and the earthquakes don't actually come very close to the seafloor. Though typically the fault region will be sort of the earthquake will originate at about 30 kilometers depth and go deeper. There are occasional what are called tsunami earthquakes, where the fault will break all the way to the trench. So you'll have motion essentially at the seafloor, and typically the trenches are 3 or 4 or 5 miles deep. You have motion of that plate above this subduction slab moving, and that's when you get a lot of motion, and it's relatively shallow. It's about 5 kilometers below the seafloor rather than 35 kilometers below the seafloor. And that's when you get the really big tsunamis. The Huku broke all the way to the trench. The trench there is about 6 kilometers deep, but it moved something like 50 meters, produced this 10-meter high tsunami offshore, this 40-meter high tsunami offshore. So when he says shallow, he means near the trench.
Yeah, very close to the seafloor. Okay. Great, thanks. Okay. So one key question is why some earthquakes rupture all the way to the trench, why some don't. Okay. And also how can we tell if, for example, one particular section of subduction zones, whether it will rupture to the trench or not. So these are the fundamental questions, challenge questions. So what the reason for that is, okay. So the reason for that is fault zones are heterogeneous. Okay, so it's usually have patches. It's segmented. And then this is a figure kind of try to show the heterogeneous where, so these big red patches, these are the places where large earthquakes happen. Okay. And then the yellowish, these are the places where fault goes relatively just smooth. They just keep going. There's no stress accumulation. And then the small patches here and there, the red ones, that's where you do get small stress accumulation, but when they release, they either release as smaller earthquakes or slow slip events. It does not generate seismic waves. It's rather slow. So that's kind of that's a trench sag. So that's kind of fundamental reason. And we want to use geodetic observation to map this. So for example, on a particular fault, which section have this shallow locking or some don't. Okay, so that's kind of the motivation. Go ahead.
Yeah, so again, speaking of learning physical oceanographer about this, I was really struck that they've mapped places where former sediments have gotten drugged underneath the plate next to them, and you can imagine that would provide some sort of catch, it would tend to catch, I think, and lock up for a bit of time, and move around there, there's smooth places that move more easily.
Right. So you're talking about why there's heterogeneous, right? So some of that come from you get rough seafloor going down to the trench. Okay.
Or just the constitution was kind of what.
Yeah.
I don't even have the right language, sorry.
Okay, that's right.
What are the spatial scales of these structures? Horizontal.
Horizontal. So next slide might show better. Oh, I'll show next slide. Okay. Other questions? Okay. Okay. So here's an example that taking Cascadia. All right. So the location is that's Washington State, Oregon, where there's a subduction zone going down below that. Then on the right, so these are two we call locking maps. These are based on on-land GPS data only. Okay, so these are only based on online GPS data, and what they do is they monitor how fast the subducting plate is going down, and then they build a model, numeric model, to explain the observation that when the plates are locked, so that's where you get these red colors. That's a place where the slab was going down with overriding continental slab at the same time. So they're locked, and then stress build up and only released by large earthquakes. And then for places like a yellowish, or even blue in these cases, there's some yellowish. Yellowish means there's no stress accumulation or very small. So the slab just going down without dragging the overriding plate with it. Okay. So what we can do with these locking maps is you can estimate future earthquake size, or estimate like how large tsunami you might generate if the fault go like full size. Okay. So to answer the question about the spatial scale, like this is one example. So this is 2 degrees, right? So that's about 200 kilometers. Okay. So the patch of its side, for example, if based on this model, there's basically 2 patches here and there. So this patch is 200 kilometers long. This one is also 200 kilometers long. But based on this model, the whole thing is locked up. The interval rupture, generate a huger tsunami. Okay. So we cannot distinguish between these 2 models using land GPS data because we don't have resolution offshore. Okay. So these 2 are kind of like end members. But if we can have geodetic, seafloor geodetic measurements offshore, like filling these places, then we will be able to tell which one is right. Okay.
So Matt, I mean, it's worth pointing out that Cascadia is a place that has very, very large earthquakes. It's had a magnitude 9 in 1700.
Yeah.
And the reason it's had a huge earthquake is that compared to other subduction zones, The stuff that's going down the subduction zone is remarkably uniform. There's a huge amount of sediment going down.
Yeah.
What that means is the plate interface looks very similar everywhere. And in situations where basically the plate interface looks similar everywhere, when you get an earthquake propagating, it's propagating stuff into a new region that's very similar to where it was. So that in places with very uniform geology, going down the slab, you get very large earthquakes. There's also evidence here of slightly smaller earthquakes, magnitude 8s, that correspond to the sort of yellow and the sort of banded red structure you're seeing on the right. This contrasts to a place like New Zealand, or a contrast to a place like Western Aleutians, where you have very, very little sediment going down. That means you have a lot of topography going down. And in that case, the fault interface is probably very ununiform in how strong it is. And in those cases, you tend to get much smaller earthquakes because you start in one region and you break through a strong region, then you go into a weak region, then you come back into another strong region, you stop.
Right.
And so that figure we saw earlier, where we're looking at red patches on the interface and yellow patches around it, that's sort of describing variable geology. And the other thing that matters is the amount of water in the interface. You can get patches of where there's a lot of water, weak sediments, and then you'll have other places without much water that are much stronger. So these are the sorts of issues that seismologists are putting an enormous amount of effort into trying to understand the patchiness of these interfaces. Because the largest earthquake you're going to get depends on how the scale of those patches.
Yes. Yeah. Right. Okay. Yes. Great. And a seafloor geology will help us to look at the patches. Okay, so that's another driver. Okay, so this is animation I found online. Talk about slow slip events, because we do have a few talks. We'll talk about slow slip events. So I think it's nice for us to take a look.
In New Zealand, the Pacific and Australian tectonic plates meet along a series of major fault lines. In the North Island, the Pacific plate dives or subducts westward beneath the North Island's east coast along the Hikurangi Trough. It forms New Zealand's largest and most active fault, the Hikurangi subduction zone. The plates move towards each other along this fault. In the deepest parts of the Hikurangi subduction zone, the rocks are hotter and the plates can move past each other slowly and continuously. But at shallower depths, the plates are more brittle and the friction between them causes them to temporarily lock together. Over time, the stress at the locked zone builds up. Every few years, the plates temporarily become unstuck and a slow slip event occurs. This releases the built-up stress and the Earth's crust rebounds. A slow slip event is like an earthquake because energy is released along a fault line, but this energy is released over weeks to months during a slow slip event, unlike an earthquake which lasts only a few seconds. You can see from the GPS sites how the land moves. Earthquakes in the subduction zone. Sometimes the movements between the plates aren't slow but sudden and fast, resulting in damaging earthquakes. Large earthquakes can occur on the subduction zone after the plates have been locked together for a long time, perhaps for hundreds or even thousands of years. Over many years of locking, enough stress and pressure builds up on the fault that eventually the fault breaks, allowing the plates to suddenly slip past each other in an earthquake. Can a slow slip event cause a major earthquake? Slow slip events often occur next to the parts of the plate boundary where earthquakes occur. Scientists are investigating how a slow slip event can increase stress on the locked segment of the plate.
Okay, I have to clarify for that. So that animation shows those events always in the below the lock zone, but that's not necessarily true. Okay, so there are places where slow events is above the lock zone, or in sometimes there's no lock zone, just those vents. Okay. See if we can find.
Slow slip events often occur next to the parts of the plate boundary where earthquakes occur. Scientists are investigating how a slow slip event can increase stress on the locked segment of the plate boundary and whether or not this can influence the timing of future earthquake ruptures. Once scientists can better understand this relationship between slow slip events and earthquakes, we might be able to use slow slip events for better earthquake forecasting in the future. However, it's important to know that we have observed dozens of slow slip events in New Zealand that have not triggered large earthquakes. Research on slow slip events in New Zealand.
Okay, I'll just stop there. All right. Many of you may recognize that our colleague Laura Wallace. Okay, all right. So as I said, slow events are not necessarily below the lock zone. They're sometimes in the shallow part. So for example, here are a few maps I'll show, like from here. So this is offshore Costa Rica, and the pink areas are the places where show slow slip events. Okay, so they are not ruptured earthquakes, but they're not like continuous. They are episodic, rather slow. So in this case, you do have lock zone here, then you do get slow event patches below and above. Okay, so for example, this might be a place where we do not expect large tsunami because near the trench, a lot of stress already been released by this slow slip. Okay, so then this is New Zealand. So in New Zealand, near the North Island here, there's even no lock patches. It's just slow slip patch in this part. Then you transit deeper when go deeper, then there are changes. But in this section, it's like that. Then here in Japan, this is also Japan. We have observations of shallow, slow slip. Okay, so in most cases, we see shallow slip, slow slip, because they are close enough to the land. So for example, in this case, you can see the Nicoya Peninsula. It's kind of going out relatively close to the trench. And that's the same case for North Island of New Zealand too. Okay, because the GPS is close enough to the source, then we can see it from GPS. But for example, here I showed this is Cascadia, this is Alaska, the Anchorage over here. Then here's Chile. Most of the coastlines are about 100 kilometers away from the trench. So anything that happened very near the trench, we cannot see it with just on land instruments. We need offshore instruments. Okay. Any question on this?
Is a slow slip event also sometimes referred to as an earthquake swarm? I've come across
No, it's a different
very
concept.
similar.
It's a different concept.
That's a different concept.
Yeah. So earthquake swarm usually is a number of earthquakes with similar magnitudes. They happen like usually it's related to fluid migration or something, but then slow events are just a movement. It's not earthquake,
Okay.
first of all, because it does not.
I've seen an example where the result looks very much like a slow slip event, where the land has moved by 60 centimeters over a few months. But
Earthquake
the
swarm.
literature described it as an earthquake swarm.
You're sure gonna have more with the slow slip events.
Yeah.
I'll show an example later.
Okay, good. Yeah, sometimes they do go together.
Yeah.
Okay, all right. So here's just one simple model. My student Ling Chao helped me did. Okay, so okay, I hope I'll explain from the left. Okay, so assuming this is a subduction zone, okay, then there's a fault going from the trench to going down. So for simplicity, the trench is flat, straight. Okay, assuming there is a 90-degree dip angle. And then if you look, so here is a map view. When you look down, look at the fault. Okay, so where we put a 10 by 20 kilometer size patch, just slipped. Okay, it slipped. We just said 1. Okay, so slip, it could be 1 centimeter, 1 meter, whatever. Okay, so here, this is the horizontal displacement going east-west. Okay, so going west is positive, so going that way. And this is vertical deformation. When it's yellow, it's going up. When it's blue, it's going down. And then there's the dashed line. We do a profile here. So the blue line is the vertical deformation. The red line is the east-west displacement. Okay, so the y-axis here shows the percentage. So for example, if the fault slip a meter, then you're expected to see about 30-ish% here. That's about 30 centimeter. Then if the fault slip 10 centimeter, then you should see 3 centimeter like this. So the key point of this figure is that if this is a trench, okay, then if the slip happened near the trench, in this case, the top is about 3 kilometer depth. That's what I said. Okay, then the deformation are all in the ocean. And then if you have a coastline, it's about 100 kilometers from the trench, you are not going to see this thing. Okay, so that's our kind of some of the targets, scientific target we want to measure. As showing the New Zealand case, a lot of times we are looking at a few centimeter of deformation max. So that's why we're looking for help from geophysical oceanographers, try to help us to reduce the water noise. Okay. All right. Time. Okay, so that's kind of one of the main driver. The other recently, there's a driver of why we care this is that so for a normal earthquake sequence, earthquake never is just one event. Okay, sometimes you get 4 shocks. So these are the relatively smaller earthquakes in that region before the big one. Okay, then after the big main shock, then you get many aftershocks. Okay, so that's a typical kind of a sequence of large earthquakes. And what people recently found is that so I show here. So these are 2 examples. One is a 2014 earthquake in South America. The red one is 2011 Kahuku earthquake. There are different colors and different signs, but the main idea of these 2 observations is that in both cases, before the main shock, so the largest one, there are 4 shocks. Okay, there are sizable 4 shocks that they produce instantaneous slip. Okay, and also in both cases they produce we call after slip. So it's basically it's a aseismic slip where the faults move without generating any seismic waves. It's relatively slow, and then what happens is you get a foreshock, then there's after slip move, then later on you get a big shock. So the idea is that the after slip actually triggered the main shock. So is it true? No, it's still in debate because all of these are relying on either on land, in that case it's on land data, and in Kahuku case there's some still debate because the data really, the signal is really small. You can argue it's there or not. Okay, so first of all, is this really happening? Okay, and also if it's happening, can we use offshore deformation measurements to, I don't know, early warning? I don't know. So there are some ideas floating around. Okay, so as I said, the whole field really motivated or advanced by the Japan earthquake. So after the 2011 Japan earthquake, Japan put huge amount of money into this field. Okay, so they built this one you call SNet, and then they have these 2 smaller sites, it's called DONET. So all these nodes, the circles, they have safer pressure sensors, and they have seismometer sensors, accelerometer sensors. So these are intended to really improve our offshore capability of monitoring deformation and earthquakes. Okay, so but unfortunately, most of the pressure data in the SNet is not usable because you have these thermal. I think they couldn't control the temperature in the casing. So the data is really noisy, unfortunately. But DONAT, as far as I know, DONAT seems to work really well. Okay, the sensors are useful. Okay. So here I list a few others that campaigns that have included pressure data or pressure sensor. So this one is Cascade Initiative. It's a 3-year project. Not all the sensors are in the water at the same time, but they kind of rotate every year. But they do cover a lot of section of Cascadia. Then on top, this is a relatively recent one. It's in Alaska, where it's a campaign. It has seafloor pressure data, but also seismic data, OBS. Okay. Then this one on the right side is New Zealand. So New Zealand, since 2014, Laura Wallace led that Hobbit network that's over here. Then her group and collaborators have did other campaigns south of that location. So here I show some of the locations. And the SPAR web, we've got to talk more about this in detail. Okay. And last year in October, we went back to the Hobbit sites and we did another campaign where we have about 40 seafloor geology network, like instruments on there. That's from, we get instruments from New Zealand, from United States and Japan. So they'll be there for 2 years, then we'll recover them. Okay, so this will be an exciting new thing. Okay, so another thing I want to emphasize that, so on the left, these are the Earthscope PBO project, which, when did it start? More than 10 years ago, probably. Then what they did is they installed over 1,000 permanent GPS stations or take over some existing instruments. So these are the, you can see how many geodatic instruments you put there. And these produced huge amount, a lot of projects, a lot of papers, a lot of findings. It's really exciting. And we're kind of in the phase of trying to do something after that. Then one idea came up is called Subaqueous 40. So on the right, this is their implementation plan where they envision what they do. So they choose southern Chile as kind of a site. And what their plan is to put both onshore and offshore instrument, huge network with both seismometers and the geodetic instrument and other things. So I guess my point is we are at a point where it's a huge opportunity of moving offshore. And I think if physical oceanographer can join us in this effort, maybe we can produce, do things that we couldn't do by our own. Okay, all right. So that's about subduction zones. Next, I'll switch a little bit to volcanoes. Okay, so this shows major volcanoes around the world. And one statistic is that 75% of volcanic eruptions happen in the ocean. Okay, so volcano is really, marine volcano is a next, like the big opportunity next. And there are some projects going on, but very limited number. So if we can reduce the cost and improve the measurement accuracy, we can probably do more. Okay, so for underwater volcano events, one is along these spreading centers, so along mid-ocean ridges. Okay, so there are a lot of these activities. Some of the relatively well-studied sites include East Pacific Rise 9 degree north, and Axial Seamount, and also Lucky Strike. In the workshop, we have a few talks. We'll talk about Axial Seamount and also Lucky Strike as well, I think. So as you can see, they are abundant, but relatively less studied. Okay. So Bill will talk about it, this Axial Seamount project. So here's the location of the site, and then these are the instruments Bill and his collaborator Scott Lunar put there for more than 25 years. Then one this is really a unique data set where they have caught 1, 2, 3, 3 eruptions of this volcano. So you can look at what happens during these volcanic cycles. This is very unique, probably the only one. Okay. All right, Bill will talk more about this. So another, I think Valerie gonna talk about this. This is a lucky strike. So this is about 600 kilometers away from Azores, where most of the instruments I think are for biologists. They try to look at the vents, but Valerie has some pressures instrument there, and she will show some exciting results. Okay, subacute zones, of course, it's one of the most important targets. Here are a few examples that have been relatively studied. Okay. Other than hotspots, so hotspots, Hawaii is a hotspots where we care about. And then here's a map of different hotspots, and there's also some well-studied sites. And this is a volcano near, where's Africa? Yeah, it's somewhere here. And Valerie also talked about that. They have some long-term observation there. Okay, so for volcanoes, why we care about measuring deformation of volcanoes? This is an animation showed what happens. Okay, so I think they made this animation based on data observed using INSAR. So it's a satellite looking at surface deformation on land, where you can see that between cycles, you get it's like a heart going up and down, the pump, right? And then the general idea is that the source of the deformation is really coming from the magma chamber, where you get fading, then you get, if there's eruption, then you get the subside. So they're going through cycles. And we expect some, like in Exosima, we do see that happening. But there are more sites where we hope to look more detail, but record these kind of deformations, and we can study the sites. Okay. All right. So that's volcanoes. Okay. I'm almost finished. Here is one thing I want to show to physical oceanographers. So this is a kind of a pilot project we did a few years ago in near Newport, Oregon. So over there, there is there's a cable going out, and there's some benchmarks where William Wilcock and Mark Zumberger, they have these benchmarks there to do pressure measurements. Then they kindly allow us to piggyback their ship. Then we go there, put 4 sea pies. So these are the 4 sea pies, and you can see that the entire distance between 01 and 03 is about 20 kilometers. So we get 4 there along the shelf, and what we hope is we can measure the pressure and also the current. Okay, current can be also helpful, where maybe Randy will talk a little bit more. So what we learned is that there are 2 things. So the first thing is, so on the left, these are pressure data, the blue line. Oh wait, the red line. The red line is the data, and the blue line is a ROMS model from Parker McGrady from University of Washington. So he generated a high resolution circulation model there, and he told us he didn't know what's going on in the deep water. He just ran it, and hopefully they match. Okay. So on the right, the red line shows the current, the measured current, and then the blue line shows the model current from Parker McGrady's model. Okay. So one thing we learned is that these physical models, they are realistic, because if you look at the magnitude of these changes and also the frequency, it looks really real, but they're not real. We couldn't just subtract the model from our data, because apparently you can see here we do not expect there any tectonic motion at that time. If there is, we're super lucky, but probably not, right? So even though, yeah, sometimes it looks really good, but there's some deviation. We cannot use it. Okay, so that's one thing we learned. The other thing we learned is small scale topography matters. So in this case, particular case, so there's 4 sites, right? So here we plot all the pressure measurements for the 4 sites together. And if you look carefully, okay, 01, 01.5, 02, these 3 looks very similar. Okay, but 03, which is a purple line, for example, over here and over here, is kind of deviate from the other 3 sets a lot. So there are potentially a few reasons, but one of the reasons I think is that if you look at topography carefully, here is a small valley that these pressure centers just sit there. So we think, in addition to the shell, it was a little bit shallower. This might play a role because I mean Parker's model probably does not have. I forgot the resolution of his bathymetry map, but that's probably too small that you cannot catch. All right. Okay, I'll stop here. Any question?